Thank you to the organizers for inviting me to give a talk. Unfortunately, I could not be there in person. So today I would like to tell you about, actually I'll start talking about surface homeomorphisms. So that's where my motivation will come from. Then I will talk about free group automorphisms, and then I will boil my problem down to some graph maps. Okay, so let's start. So my motivation comes from surfaces. So I want to start with a closed surface of genus G, where G is at least 2. So I'm starting with this surface of genus at least 2. I want to look at a particular homeomorphism of the surface, which is called a pseudo-Nosov homeomorphism. What this homeomorphism does is, locally in a chart, it basically stretches in one direction and it contracts in the other direction. So locally in every chart, I have 2 foliations. Like I can foliate my chart by horizontal foliation and vertical foliation, such that the horizontal one is getting stretched and the vertical one is getting compressed. And the number by which the stretching and compressing is happening, there is one number by which you are stretching and compressing. So this is the definition of this kind of surface homeomorphisms. So I'm considering these particular surface homeomorphisms, which have 2 invariant foliations, which I call stable and unstable foliation. One of them gets stretched, the other one gets contracted by the same number, lambda phi. I call this lambda phi the geometric stretch factor because it's stretching my surface. I can also look at the map induced by this homeomorphism in homology, and that's a linear map. And there I can look at the spectral radius. I can look at the absolute value of the largest eigenvalue. And I call that number the homological stretch factor. So I have these 2 numbers, geometric stretch factor and homological stretch factor. It's clear that the homological stretch factor is always less than equal to the geometric stretch factor, because I might lose some information in homology. When I pass to homology, I might lose something. So homological number is less than the geometric number. But then the question is, when are they equal? And this question was answered by work of Thurston and Van Boylen. So they basically considered a pseudo-Nosov homeomorphism on a surface of genus. So I'm always thinking genus at least 2. And they showed that these 2 numbers are equal. And a way of thinking about this is that the homological data determines the geometric data. Homology is always easier to work with because then I'm reduced to a linear map. So this homological data determines this geometric data if and only if the foliations that I talked about, they are transversely oriented. So what does that mean? So let me just do an example of something that is not transversely oriented. So I've drawn one of the foliations. There are some singularities in the foliation because I'm working with genus at least 2 surfaces. And a transverse orientation would be like if I go around a loop in this 3-pronged singularity, if I start giving a transverse orientation to my leaves, and if I wanted to go around compatibly, then when I come back, there is a clash of orientation. So if I have this 3-pronged singularity in my foliation, that means my foliation is not orientable by this definition. And Thurston and Van Boylen showed that these 2 numbers are equal if and only if I don't have this bad behavior. So if and only if my foliations are oriented in a nice way. So there is some notion of orientation on the foliations, and if the foliation is orientable, then these numbers are equal, if and only if. So then like I was saying before, the guiding question here is, when can topological invariance of a surface homeomorphism be recovered from its homological data? And in the surface case, like higher genus case, the homological data determines the topological data, the stretch factor, if and only if the foliations are orientable. So that's the motivation with which we started this project. But I am interested in, free group automorphisms. So let's see. Oops. So I am interested in free groups. So I think of a free group of rank n as the fundamental group of a wedge of n circles. And I am interested in, I'm replacing my surface with this wedge of circles. So I'm looking, instead of surface groups, I'm looking at free groups. And instead of looking at surface homeomorphisms, I want to look at free group automorphisms. And often I look at something called outer automorphisms. And that just means that I'm looking at automorphisms, but I'm quotienting out by the inner automorphisms, because inner automorphisms are just conjugation by an element of the free group. So that's isomorphic to the free group. So I usually quotient out by that group, and then try to understand group of outer automorphisms of the free group. So this is the main, these are the free group automorphisms are the main things that I'm interested in. And here I'm especially interested in something called a fully irreducible free group automorphism. So I'll show some examples. I'm particularly interested in fully irreducible. So these are the analogs of pseudo and Nassau homeomorphisms. So I'm interested in these free group automorphisms. I can show you the definition, but I think the example will be more helpful. The definition is, a free group automorphism is called fully irreducible if basically you should think it's mixing. Like that pseudo-Nassau homeomorphism was also mixing. Like if I start with a simple closed curve, it will, as I keep applying my automorphism on it, it will send the curve everywhere. And here also, I want this automorphism to be mixing in the sense that no power of phi preserves the conjugacy class of any proper free factor. So I don't want my automorphism to preserve any free factor. I want it to mix it up. And maybe I should say, what is a free factor? A free factor is basically, if I write my free group as a free product of two subgroups, then those subgroups are called free factors. So I'm looking at free group automorphisms, a particular kind called fully irreducible, which are the ones which mix up all the free factors. They don't preserve any free factor. So here are examples, non-example first. So if I look at this, so I'm thinking of my free group F3 as generated by A, B, and C. So to write a free group automorphism, I just have to say where the basis goes. I have to send a basis to another basis. So I'm sending A to B, B to A, and C to CA. And this is a basis because you can see I can recover A, B, and C if I just play with these three words. So that's good. This is a free group automorphism. Is this fully reducible, or is this preserving a free factor? So in fact, it is preserving this free factor generated by A comma B. It's because, why is this a free factor? Because I can write my free group as a free product of the subgroup generated by AB and the subgroup generated by C. And my automorphism is preserving, it's switching A and B, but it's preserving this subgroup. So this is not a fully reducible free group automorphism. And here is an example of something that is fully reducible. It's harder for me to justify this, so maybe I'll just leave it at showing you the example. A goes to B, B goes to C, and C goes to CA. This one's supposed to be mixing enough. Okay, so now I have my particular free group automorphism. I want to associate two numbers to it again, similar to the surface homeomorphism setting. So the first number I associate is basically, let's do it step by step. I look at a word in my free group. I look at powers. I apply my automorphism to it. I look at high powers of the automorphism applied to the group. And this is word length with respect to any basis. I'm just counting word length with respect to some basis. And then I take this rth powered, I take the limit, and then I take the supremum over all the words. So what is this is measuring how fast W is growing. And I want to just see the fastest growth over all the words of the free group. So this is growth rate of, well, I guess I should have said conjugacy classes, but let's just ignore the out stuff and the conjugacy class business. So I'm measuring growth rate of elements of the free group, and I call this the geometric stretch factor of my free group automorphism. It's just measuring the growth rate of words. So here is an example. I'm looking at this. So this is my example from the previous slide. This is my fully reducible automorphism. A goes to B, B goes to C, C goes to C. Now, if I start with A, so A is W for me. And if I keep hitting it with phi, so I get A goes to B, B goes to C, C goes to CA, CA goes to CAB, and so on. And I want to count. I want to like see how fast this is growing. So this is 1, 1, 1, 2, 3. This is the word length. This is word length 3, and so on. So how do I count this? I can write a matrix. I can write a matrix which keeps track of my map. So the matrix is basically the first column corresponds to A, and let's see, first row also corresponds to. So the first column is basically that A is mapping over B once, and it's not mapping over A and C. Then B is mapping over C once, and C is mapping over C and A once each. So that's the matrix I associate to my automorphism. And I can think of my word A as a vector. It's the vector 1, 0, 0. So A, B, C are my basis for the free group. And now like in this vector sense, like the 3 vectors, and then A is the vector 1, 0, 0. So now if I apply so what this norm is also L1 norm. This is L1 norm. Okay. If I apply powers of M to my vector VA, you'll see that's basically, and if I look at the L1 norm of that, L1 norm meaning just count, just sum up the entries of that vector. Everything is positive here. That's the same as counting the word length of phi to the n of A. So again, just like applying the matrix to the vector VA and doing L1 norm is the same as counting the word length of this automorphism applied to A in this example. So this lets me compute. So basically, if I wanted to compute the growth rate, not with the supremum yet, but if I just wanted to compute the growth rate of phi to the n of A, I could just do the growth rate here. And in fact, like if I do supremum over all A's, I would just be computing the spectral radius of M. So the growth rate here would be lambda phi would just be the spectral radius of M, be the top eigenvalue of M. That's the growth rate for this automorphism. So that's the first number, geometric stretch factor. The second number is, again, I can pass to homology. I have my automorphism. I can look at the induced map in homology of the free group. That's again a linear map, and I can talk about its spectral radius. So again, I have these 2 numbers, geometric stretch factor, which is measuring the growth rate of elements of the free group. And then I have this spectral radius of the map induced in homology. Okay, this is maybe, let's take this as a fact that for these fully reducible automorphisms, the stretch factor is always strictly bigger than 1. It's like they're mixing everything up, so somehow they have to stretch things enough. And again, it's clear that the homological stretch factor in homology, you might it's possible that the map is in fact trivial in homology. If I was, so the homological stretch factor is always bounded from above by the geometric stretch factor. So as with the surface homeomorphism case, I asked the question, when are these 2 numbers equal? So again, when can I use the number from homology to just figure out the number in the geometric number, the stretch factor? And why is this useful? Because this is a straightforward thing, the spectral radius in homology, but for this stretch factor, somehow in my example, the M worked out nicely the M was all positive, there was no cancellation happening anywhere, that I got this equality. But in general, I might not be able to do this for arbitrary automorphisms. So it would be nice to know when these two numbers are equal. Okay, so I'll show you our result, and then I'll define some things in there. Okay, so I'm starting with a fully irreducible free group automorphism to the same setting. And then the following are equivalent, that the geometric stretch factor is equal to the homological stretch factor if and only if phi has a orientable graph map representative. So I have to tell you what is a graph map representative of an automorphism, and I have to tell you what it means for it to be orientable. So that will be the rest of the talk. And then I'll show you the last statement, but I'm not really going to talk about this. So there are these special graph map representatives called train track representatives, which are the good ones. So the example I showed you was actually a train track representative, but we'll not talk too much about these. So remember the surface theorem? The surface theorem was the two numbers are equal if and only if the foliation is orientable. And here our result is that these two numbers are equal if and only if there is a graph map representative that is orientable. So now let me tell you what is a graph map representative of an automorphism and what does it mean for it to be orientable. So graph map representative is basically something very simple. Like I'll do some silly examples, in fact. So this is my free group automorphism. Here again, F3 is generated by A, B, and C. I can think of this free group automorphism as a graph map where I'm starting with this graph, wedge of 3 circles. I'm labeling the edges by the generator. So the edges are labeled A, B, and C. And I can say that the graph map is that it sends the edge A to the edge B, the loop B to loop C, and then the loop C to the edge path C, A. Sorry, forget the green stuff for now. So this is a graph map representative. I've just written, why am I calling it a graph map representative? Because the induced map on pi1. Like if I look at the map induced by F on the fundamental group, then I exactly get phi. So it's a graph map whose induced map in fundamental group is the automorphism I started with. So it's called a graph map representative. Let's look at another graph map representative. So this is slightly more complicated. Now I'm looking at free group of rank 4, generated by A, B, C, D. And I'm sending, so okay, A to B, B to C, and so on. But D is going to slightly more complicated word. And then I can again define a graph map where I basically do the same thing. I send loop A to loop B to loop C, and so on. So the point of these two, showing you these two examples, is that in the first example, this first example is what we did. What we did here. So if I want to compute the growth of conjugacy, growth of elements of the free group, I can do this matrix business. I can write this matrix and find its eigenvalue. For this example, it's the same example. This computes the growth rate correctly. However, in this second example, something goes wrong. So I claim that in this second example, if I write the matrix and if I just like apply the matrix and try to see how it grows, it's not going to give me the correct thing. Why? Because now if I look at D maps to, I should have said A bar means A inverse. Sorry. A bar means A inverse. So D maps to A inverse, like this word. Then I apply phi again. It maps to this long word. But now there is cancellation. And so for in the free group setting, like if I'm counting the word length, I'm actually only going to count this much. But if I was doing the matrix business, I would actually end up counting these two as well. Because when I do the matrix stuff, I have no way of keeping track of cancellations. So here I would not like this graph map representative is in a way not good, because the matrix coming from this graph map is not going to give me the right growth rate. So there are some graph map representatives are good, some are bad. The good ones are called train tracks. Okay. So now the second thing, I need to tell you what it means for a graph map to be orientable. So let's start with a graph. An orientation on the graph is a choice of orientation on each edge. So that's those little arrows that I've been putting. And I say a graph map is positively orientable if there is an orientation on G such that F sends positive edges to positive edge paths. And I say it's negatively orientable if I send positive edges to negative edge paths. So I'll show you examples in a second. And it's called orientable if it's either positively or negatively orientable, and it's called not orientable if it's neither. So let's look at examples. So here is an example of a positively orientable graph map. Each edge with this given orientation, it's mapping to, so A, B, C are the positive orientations, and they in the image, I'm seeing only the positive edges. So this is a positively orientable graph map. Okay, I've switched notation. Now capital letters mean inverse, sorry. Here, here what's happening is the little ABC are my chosen orientation, edges with chosen orientation. But in the image, I'm seeing all the edges with opposite orientation. So this is C bar, like C traverse in the opposite direction. So this is negatively orientable. And something that is not orientable would be this. So A goes to BA, B bar, B inverse, and C. So here I'm seeing B and B inverse both in the image. And no matter how I switch these arrows around, I'm never going to get rid of seeing both B and B inverse. So this is a non-orientable graph map. Okay, so now before I go back to my automorphisms, I need to talk about stretch factors of graph maps. So we kind of did an example. So I'm starting with a graph map. I can write a transition matrix for my graph map. The transition matrix is basically the matrix where in each column, I just count, or each Aij is the number of times Ei crosses Ej crosses Ei in either direction. So for this transition matrix, I don't care about orientation of edges. I just want to count how many times I crossed an edge. So let's quickly write these matrices for these examples. So A here would be, so A crosses B once, C1, B crosses C once. Here, A would be A, B, C. So now A is crossing C in a negative orientation, but I don't care. I just want to record that it's crossing C once. B is crossing this and then this. And here it would be 1, 2, 1, 0, 0, 1, and 1, 1, 0. So I don't care about the orientation for transition matrix. Now I can look at the map induced in homology or on one chains. I think I should say not homology, the map induced on one chains. And you should be thinking I'm abelianizing my map, and I call that matrix M. And Mij is basically the number of times Ej crosses Ei with orientation. So now, let's see. So here, M would be the same because everything is being crossed with positive orientation. Here, M would be minus A because now I'm keeping track of orientation. And here, M would actually be very different. So now A, B, C. I've passed to one chains now. So now A is crossing A once, B 0 times, and C once. Why is this 0? Because it's B and B inverse, and now I'm keeping track of orientation. And so on. So I have these two matrices, A and M, and I I say lambda f is the spectral radius of A and lambda rho f is the spectral radius of M. And it's clear that Mij in absolute value is less than Aij, because for M, I'm counting orientation. So it's clear that this homological spectral radius is less than the lambda f, the stretch factor. So at the level of graph maps for these two matrices, it's clear that rho f is less than lambda f. So what we show for graph maps, so if I start with a graph map with transition matrix A, but not just any graph map, I want the strong property of my transition matrix being primitive. So this means that like A is primitive if there exists an n such that A to the n is positive, meaning every entry of A to the n is positive. So for such graph maps, I say that these two numbers are equal if and only if f is orientable. So it's either positively orientable or negatively orientable. So one direction is easy. If f is orientable, so if I'll just go back to the examples. Sorry, let me make it smaller for a second so you can see both. If f is orientable, so here A is equal to M, so clearly their spectral radii are equal. A is equal to minus M, so the spectral radii are still equal. The spectral radii, you take absolute values. Here A and M are not equal. So all I was saying is, if my map is orientable, then the fact that these two numbers are equal is obvious. But then the other direction is what we prove in this theorem. So for these graph maps with primitive transition matrix, we have this homological data determining topological data if the map is orientable. So just like, let me show you our result again and put it in context. So our result was that if you have a free group automorphism, special kind, this fully irreducible, this mixing thing, then these two numbers, the homological stretch factor and geometric stretch factor, are equal if and only if I can find some graph map representative, so some graph map whose induced map in pi1 is free, that is orientable. And the last bullet point is, if I can these good graph map representatives, if they are orientable if and only if these two numbers are equal. And I think I'll stop here. Thank you.
Thank you, Radhika. Are there any questions?
Hi, Radhika, this is Riddhi. I missed some of your talk, but I was just wondering, when you write this metric representation, it looks like as if the free groups are abelian, but that's not true, right? So
right. So that's what I was like. I did one example, like here in this example, where my automorphism was this. I was saying that like I could write the matrix here. Like I could write the matrix A, where A, B goes to C, C goes to D, and then D goes to like all the four letters. So I could write this matrix, but this is not a good way of counting how fast my D is growing under applications, because as a free group automorphism, there is cancellation that I'm seeing. But in this matrix, I'm not going to be seeing that.
But even the first one you wrote, where you wrote MVA, there also it like AC and C are same, right?
Yes.
Yeah, that one.
Yeah. So I'm using this matrix only to count stuff.
Okay, I see. Okay.
Yeah, you're right. Like this makes it sound like things are abelian, but I'm only using these to count stuff, because obviously CA is not equal to AC. Yeah.
So is there any count on like how many outer automorphisms you'll get for free groups? I mean,
can you ask the question again?
How many outer automorphisms can you get? I mean, uncountably many or countably many?
So the group of, let's see, let me write here. This group,
Yeah. Yes.
this
So
group is finitely presented.
finitely presented. Okay.
So it's,
Is it because of finite number of generators or?
yeah, it is finitely generated and finitely presented. So I guess it's a countable group.
Okay. So you get all kinds of things here with growth and so on. I mean, you have some growth property for.
Right. So we get a polynomial growth or exponential growth
Thank you
for
very
these
much.
conjugacy classes.
Okay. Thank you very much.
Thank you.
Any other question?